In 1969, when the Apollo astronauts left their footprints on the lunar surface, they also left behind something unexpected: mirrors. These weren't for the astronauts to check their appearance before the photo ops, but rather for scientists back on Earth to bounce lasers off of. Why? Because since the dawn of time, our celestial companion has been slowly, but steadily, drifting away from us. These mirrors would finally give us the precision to measure exactly how fast. The results? Our moon is moving about 3.8 centimeters away from Earth every year, roughly the same rate at which your fingernails grow. It might not sound like much, but this subtle change represents one of the most significant long-term shifts in Earth's cosmic neighborhood. And recently, scientists have discovered that this drift isn't as consistent as we once thought. The moon's orbit is changing in ways that have sparked both scientific curiosity and, inevitably, dramatic headlines questioning if Earth might be in danger. But what's really happening up there? And should we be concerned? The relationship between Earth and the Moon is one of the most beautiful cosmic dances in our solar system. For billions of years, these two celestial bodies have been locked in, a gravitational embrace that's far more complex than most people realize. The Moon doesn't just circle Earth in a perfect circle. Its orbit is elliptical, meaning it moves closer and then farther from us throughout its monthly journey. And this elliptical path isn't fixed in space either. It wobbles, shifts, and evolves due to a multitude of gravitational influences, from Earth's not-quite-spherical shape to the gentle but persistent pull of the Sun, and even the distant giants like Jupiter. This complex orbital pattern has profound effects on our planet, most visibly in the ebb and flow of our ocean's tides, but also in stabilizing Earth's axial tilt, which gives us our reliable seasons. But recent measurements have confirmed what some scientists have suspected for years: the Moon's orbit is changing in ways that go beyond its expected long-term drift. In 2020, analysis of decades of laser-ranging data revealed subtle but unmistakable anomalies in the Moon's orbital behavior. These changes are small. We're talking about differences of millimeters in some cases. But in the precision-oriented world of orbital mechanics, these discrepancies matter enormously. Some of these changes appear to be accelerating, while others show cyclical patterns that don't quite match our established models. So what's causing these unexpected shifts? The answer involves a fascinating blend of factors, from the gravitational interactions with other planets to the surprisingly significant effects of Earth's shifting mass as glaciers melt and sea levels rise in response to climate change. The primary driver behind the Moon's retreat from Earth has been understood for centuries. It's all about the tides. The Moon's gravity pulls on Earth's oceans, creating bulges of water on both the near and far sides of our planet. As Earth rotates, these bulges act like a brake, gradually slowing our planet's rotation. Due to the conservation of angular momentum, the same principle that keeps a spinning ice skater going when they pull in their arms, this lost rotational energy doesn't just disappear. Instead, it gets transferred to the Moon, pushing it into a slightly higher orbit and increasing its distance from Earth. It's a remarkable system of energy transfer that's been happening for billions of years and has already slowed Earth's rotation considerably. Days on early Earth lasted just 5 to 6 hours, compared to our current 24. Now let's talk about those unexpected changes scientists have detected. Using incredibly precise measurements from the Lunar Laser Ranging Experiment, where we bounce lasers off those mirrors left by the Apollo astronauts, researchers have detected variations in the Moon's orbital behavior that don't perfectly match our theoretical models. Some of these anomalies appear to be linked to redistributions of mass on Earth. As climate change melts polar ice and causes sea levels to rise, it subtly alters Earth's gravitational field, which in turn affects the Moon's orbit. It's a remarkable, demonstration of just how interconnected our planet is with its cosmic environment. Other variations might be related to changes in Earth's core, although these are harder to measure and remain somewhat theoretical. But what does this mean for life on Earth? Is there cause for concern? The short answer is no, at least not for a very, very long time. The changes we're observing are incredibly small and develop over enormous timescales. Even with the accelerated retreat we're measuring, the Moon won't drift to a significantly different position within our lifetimes, or even within thousands of human generations. But that doesn't mean these changes are insignificant. The Moon plays a crucial role in stabilizing Earth's axial tilt, which gives us our seasons and a relatively stable climate. If the Moon were to somehow vanish or drastically change its orbit, Earth's axis could wobble much more dramatically, potentially causing extreme and unpredictable climate shifts around the globe. To put things in perspective, the Moon is currently about 384,400 kilometers away from Earth on average. At its current rate of retreat, even accounting for the subtle accelerations we've detected, it would take millions of years for this distance to change significantly enough to affect our planet's climate stability. That said, the very long-term outlook does show some interesting possibilities. Computer models suggest that in roughly 50 billion years, the Moon would drift so far from Earth that it would escape our planet's gravitational pull entirely. Of course, this is purely theoretical, as our Sun will have long since exhausted its nuclear fuel and expanded into a red giant by then, likely engulfing both Earth and the Moon around 5 to 7 billion years from now. The subtle changes in the Moon's orbit have also revealed fascinating insights about Earth's interior. Because gravitational interactions depend on the distribution of mass, measuring the precise details of the Moon's motion allows scientists to infer things about our planet's internal structure that would otherwise be impossible to detect. Recent anomalies in lunar orbital data have led some researchers to propose new ideas about flows in Earth's liquid outer core, the dynamics of the boundary between the core and mantle, and even the possibility of previously unknown layers or structures deep within our planet. It's remarkable to think that by watching the Moon's movement with precise enough instruments, we can learn about regions of Earth that lie thousands of kilometers beneath our feet. Another intriguing aspect of the Moon's changing orbit relates to eclipses. The perfect alignment that allows for total solar eclipses, where the Moon appears exactly the same size as the Sun from our vantage point, is actually a cosmic coincidence. The Sun is about 400 times larger than the Moon, but it's also about 400 times farther away, creating this perfect visual match. However, as the Moon continues to drift away from Earth, its apparent size in our sky will gradually diminish. In roughly 600 million years, the Moon will appear too small to completely cover the Sun, meaning total solar eclipses will no longer occur. Instead, every solar eclipse will be an annular eclipse, with a ring of the Sun's surface visible around the Moon's silhouette. So why have some reports suggested that these orbital changes might pose a danger to Earth? Much of this stems from a fundamental misunderstanding of the timescales involved. Changes that take millions or billions of years to develop can sound alarming when reduced to simple statements like, "The Moon is moving away from Earth." Additionally, some reports have conflated the long-term orbital drift with shorter-term cyclical changes in the Moon's orbit, such as the 18.6-year nodal cycle, which does influence tidal patterns and can temporarily increase coastal flooding risks when combined with rising sea levels. But even these shorter cycles represent natural variations that Earth has experienced countless times before, not new threats arising from the Moon's gradual retreat. That said, there are some legitimate concerns about how the Moon's changing position might interact with human-caused climate change. Higher sea levels mean that the normal tidal effects of the Moon, which aren't changing dramatically, can reach further inland and cause more flooding than they would have historically. This isn't because the moon is doing anything different, but rather because humans have altered Earth's systems in ways that amplify the moon's existing influence. In some coastal areas, the combination of sea level rise, land subsidence, and the 18.6-year lunar nodal cycle could create particularly challenging flooding conditions in the coming decades. Scientists call this a wobble in the moon's orbit. But it's important to understand that this wobble isn't new or unusual. It's just that its effects on human settlements are becoming more noticeable as sea levels rise. Looking into the far future, the moon's retreat will eventually have more significant consequences for Earth. As the moon drifts farther away, its stabilizing effect on Earth's axial tilt will gradually diminish. Earth's axis currently tilts at about 23.5 degrees, giving us our seasons and a relatively stable climate system. Without the moon's gravitational influence, computer models suggest that this tilt could vary chaotically from 0 to nearly 85 degrees over millions of years. Such dramatic shifts would cause extreme climate variations, potentially making parts of Earth periodically uninhabitable. However, this scenario lies billions of years in the future, long after other factors, like the sun's increasing luminosity, would have already rendered Earth uninhabitable. There's another fascinating aspect to the moon's orbital evolution. It wasn't always drifting away from us. Early in the Earth-Moon system's history, when our planet was spinning much faster, the moon was actually moving toward Earth. It wasn't until Earth's rotation slowed to about 24 hours that the tidal forces began pushing the moon outward, rather than pulling it inward. This turning point occurred billions of years ago, and since then, the moon has been steadily retreating. Some theoretical models suggest that in the very distant future, as Earth's rotation continues to slow, another reversal might occur, causing the moon to begin approaching Earth again. However, this would happen so far in the future, tens of billions of years from now, that our sun would have long since evolved into a white dwarf, fundamentally changing the entire solar system. Ancient astronomers and timekeepers understood the importance of the moon's regular cycles, using them to create calendars and predict tides. But they couldn't have imagined the subtle dance of gravitational forces that modern science has revealed. The moon's orbit is affected not just by Earth, but by the Sun, Jupiter, Venus, and even the subtle bulge of Earth's equator. All these factors combine to create a complex orbital pattern that includes the gradual retreat we've been discussing, as well as various wobbles, nods, and precessions that occur over different timescales. It's a testament to modern science that we can measure these effects with such precision that we can detect changes of just a few millimeters in an orbit spanning nearly 400,000 kilometers. Perhaps the most profound aspect of the moon's changing orbit is what it tells us about the long-term evolution of Earth-Moon system. Both bodies have been intimately connected since a Mars-sized object collided with the early Earth about 4.5 billion years ago, spraying debris that eventually coalesced into the moon. This violent beginning created a relationship that has shaped both worlds ever since. The early moon orbited much closer to Earth, appearing far larger in our ancient skies and creating enormous tides that may have played a crucial role in the emergence of life by alternately flooding and exposing tidal pools where complex chemistry could develop. As the moon has gradually retreated, its influence has changed, but it continues to be essential for Earth's habitability through its stabilizing effect on our planet's axial tilt. So, is Earth in danger because the moon's orbit is changing? Sahard, answer is a clear and definitive no, at least not on any timescale relevant to human civilization. The changes we're observing represent the continuation of processes that have been occurring for billions of years. They're happening so gradually that even thousands of generations from now, the moon will appear virtually unchanged in our sky. What these orbital shifts do offer us, however, is a fascinating window into the complex and beautiful dynamics of our planet's relationship with its nearest celestial neighbor. They remind us that even seemingly permanent features of our cosmic environment are actually in constant, if imperceptibly slow, motion. The dance between Earth and Moon continues, as it has for billions of years. Not a cause for alarm, but rather for wonder at the elegant, evolving system we're privileged to observe.